Okay, welcome everyone. We will continue with the discussion on the EM algorithm. So, for the sake of continuity, we will reiterate the EM algorithm and then we will look at the convergence proof of the EM algorithm. So, recall that. So, let us write down the expectation maximization algorithm for maximizing the likelihood. Expectation maximization algorithm. Now, in the EM algorithm, the idea is to maximize the log likelihood via maximizing the lower bound that we have constructed. So, please recall that we constructed a lower bound on the evidence that we called as evidence lower bound, which was given by the expectation of log of the joint distribution between the observed and the latent variable divided by QZ, and the expectation was with respect to QZ. And this distribution QZ, we refer to that distribution as the variational distribution for the nomenclature wise. Now, please note that in the last class we also saw that the optimal value functional form for the variational distribution is the posterior of the latent variable given data. So, we also saw this the last class, correct. Now, EM algorithm is an iterative algorithm that we saw. So, let us write down the EM algorithm. EM So, before I write down the EM algorithm, there is a specific note that I have to make here is that now suppose we are constructing the variational distribution at a particular theta, okay. We should note that the variational distribution that we are constructing is also a function of the parameters theta, okay. Therefore, suppose we evaluate the evidence lower bound f theta at some theta t. So, what do I mean by that? I will just clarify the notation first before we go on. So, this means that we are computing this particular expectation is equal to the expectation of this entire function, okay, with the variational distribution fixed at p theta t of z given x. This will be my notation. I will write that as f theta of q evaluated at theta being equal to theta t. So, when I write this, what I mean to say is that this f theta of q, the variational distribution that I am computing, is being evaluated at theta equal to theta t, and the q function, okay, or the variational distribution is set with theta equal to theta t. Is this notation clear? Because this is very important, because as we write down the EM algorithm, we will have to ensure that the notations are correct. So, please note that this f, which is the variational distribution, has the evidence lower bound has a dependence on theta through this numerator term and has a dependence on q. So, and the q function also is dependent on theta. So, what I mean to say is I can compute the q function at a particular theta, okay, and I can compute the evidence lower bound at a different theta. Okay, this is a key point that I want you people to note, because as we write down the EM algorithm, we will use this multiple times. Okay, so notation wise, let me rewrite it. Now, q of z can be evaluated, or rather q of z and f theta of q can be evaluated at different values of parameters theta. This is very important, and whenever I write the algorithm I will ensure that I use this. So, both of them are functions of theta, so one can compute or evaluate these two functions at different values of theta. So, please remember this. Okay. Now, with this let us write down the EM algorithm. Now, EM algorithm now initialize theta 1. So, we start with some theta 1, this is what we have initialized with. Now, for t equal to 1 to convergence, do the following. Now, note what we do. First we set the t plus first variational distribution to be equal to the posterior that is evaluated at theta t. So, please note that we are operating at the tth iteration and our goal is to find the parameters for the t plus first iteration. So, the goal is to find theta t plus 1. To find theta t plus 1 we will start at theta t. Oh sorry, this is z given x. Okay. So, the first thing to do in the EM algorithm is to find the variational distribution at time t plus 1, and that is given by the posterior that we have computed at theta t, the parameters that we already have. Okay. Now, what we do is that we compute the evidence lower bound, okay, using q t plus 1 as the variational distribution, and you make it a function of theta. Okay, what does this mean? This means you compute the expectation of log of p theta x and z divided by q t plus 1, okay, this is with respect to t plus 1. So, please note that this q t plus 1 has been computed using theta t as the parameters. This evidence lower bound is still a function of theta. Why? Because its numerator has p theta x comma z in it. Does it make sense now? Right. So, this is the E step. This is the E step in the EM algorithm. Okay. Once we do this, we will find in the M step, find theta t plus 1, okay, as the maximizer of the lower bound that we have computed using q t plus 1 as the variational distribution. This is the M step. Now, we got theta t plus 1. So, this is N for. So, this is the EM algorithm. So, what are we doing? We start with initialize with some theta, okay. At the tth iteration we find the variational distribution. So, the goal is to find the parameters at t plus 1. We find the parameters at t plus 1 by first constructing the variational t plus first variational distribution as the posterior with the current parameters, and then we find out the lower bound on the evidence by computing this particular expectation, okay, with respect to q t plus 1 that we have constructed, and this lower bound that we have constructed now is a function of theta as well. Therefore, we can optimize that with respect to theta, and in M step we find the next t plus 1, the parameter set theta t plus 1 that we need as the one that maximizes this evidence lower bound that we have just constructed in the previous step using the variational distribution computed at t plus 1, right, and then we get theta t plus 1 and we iterate. Come again, compute. Oh sorry, yeah, this is, I changed the rotation again. Okay, fine, thanks for that correction. This should be, this is, yeah, it's computed at qt plus 1. Thanks. Looks like I am cursed today, really bad. Okay, so f theta of qt plus 1, this is the EM algorithm. Is it clear now? Any questions here? Okay, so we are, yeah, so now we have to see why the EM algorithm works, okay, which is the convergence. So this convergence does not guarantee that the likelihood keeps increasing. So here is the question, what we are doing is we constructed an iterative algorithm that would maximize the lower bound on the likelihood function that we would want to optimize. Now our actual original goal is to maximize the likelihood. Why would this iterative algorithm lead to our goal of maximizing the likelihood is the question. It turns out that this particular iterative algorithm, the way we have constructed, will ensure that the likelihood function never decreases as we get the new set of parameters. So that is what is referred to as the convergence proof of the EM algorithm in practice. So we have to show, the claim is that with the EM algorithm that we just saw, the likelihood function that we evaluate at theta t plus 1 is at least equal to the likelihood function that we have gotten at theta t. So that is what is to be shown. Here is how the proof goes. So we are starting at theta t, right, in the EM algorithm we start with theta t and we put qt plus 1 to be equal to the posterior that we have evaluated at theta t, correct. Now by construction, once you make the variational distribution equal to the posterior, we know that the likelihood that we have computed at, or likelihood at theta t, is equal to the evidence lower bound. Does that make sense? Okay. So this actually means, yeah. Yeah. So why is this true? This is true because with qt plus 1 of, if you compute the lower bound, okay, such that the variational distribution is equal to the posterior, then the lower bound will become tight. That is what we have seen in the last class, and therefore this equality holds. Okay. Then in M step what do? We deliberately find theta t plus 1 such that the lower bound that we have computed in the previous step is maximized, right. That is what the M step will do. So what would that entail? That entails that if you take the lower bound that we have computed with respect to qt plus 1 as variational distribution and evaluate that at theta t plus 1, then that is greater than the same function being evaluated at theta equal to theta t. Why is that? That is because that is how we have found the theta t plus 1. So please recall the discussion that we just made, that this f theta is a function of theta and you can evaluate that at a particular theta. Now once you get the new theta, which is theta t plus 1, if you evaluate that function at theta t plus 1, by construction you have ensured that the elbow or the lower bound that you are evaluating at theta equal to theta t plus 1 is greater than f theta that you have evaluated at theta equal to theta t. And note that both of these have been computed with the exact same variational distributions, which is qt plus 1. We are not changing the variational distribution qt plus 1, we are only maximizing that with respect to the theta variable. Okay. Now if we combine all of this, okay, we also know that the at theta equal to theta t plus 1, we will ensure that the likelihood function that we compute at theta t plus 1 is always greater than the evidence lower bound, because by construction or through Jensen's inequality it will ensure that the evidence lower bound is always lower bounded by the likelihood function. Okay, this completes the proof. This ensures that the likelihood function that we evaluated theta t plus 1 is always greater than or equal to the likelihood function that we have gotten at theta t. Okay, that completes the proof, the claim that we just made, that the likelihood function would never decrease if we run the EM algorithm. Okay, now this is a sort of see, note that this inequality is not strict. What we are saying is that the likelihood function is not guaranteed to increase continuously. It is only guaranteed that the likelihood function does not decrease as you run the EM algorithm. This is one of the known drawbacks of the EM algorithm, right? So it can get stuck in the local minima because it can, the inequality is not strict. The other question that was asked in the previous class was, what is the stopping criteria, right? So typically the stopping criteria is that you run the EM algorithm and keep tracking what the likelihood function is. Now compute the difference between the likelihood at the next iteration and the previous iteration and keep a bound on that. If the difference is significant enough, then you continue to the next step, or for a, let's say for few steps the difference is not significant, then you stop the algorithm. That is how it is done. So that is a hyperparameter. So you choose choose a delta and you say that only if the difference, the improvement that we get in the likelihood function is more than that delta, I will continue, otherwise I stop. That is how it is done in practice. It's okay? Yeah? Okay. So now,
just one last thing. Could you show the slide you have? To get the last implication, are we using Jensen's inequality, or we are using the fact that the assumed form of Q, for that f theta qt plus 1 is equal to L theta plus 1?
we are using Jensen's inequality, because equality will become only if we evaluate that at the qt that we have computed with theta t plus 1, which is qt plus 2.
Oh, okay.
This is only through Jensen's inequality. You get right? The elbow evidence lower bound will match the likelihood only if you have computed the variational distribution to be equal to the theta at which you are computing the elbow. Otherwise it is not equality. It's clear, no? Yeah. Oh, you are asking what the convergence, what the stopping criteria is? No, not for f theta. The convergence criteria is the following, right? You get see this, if you look into this as a black box, every iteration it will give you a new set of parameters theta, right? Now, when do you want to stop this? You want to stop, every time you get the new theta, evaluate the likelihood, find L, okay, and see if your L is improving by a significant margin, which is user defined. If it improves with a significant margin, then continue, otherwise you stop.
And if it decreases, you still continue.
It will not decrease, no, by construction. So you just we have just shown that the likelihood cannot decrease with EM.
No, but optimization parameters, I get some set of.
I am not talking about parameters, I am talking about likelihood. Compute the likelihood at that particular parameter theta. What you compute is this L of theta. See, L of theta cannot decrease. As you are running the EM algorithm, L of theta will not decrease. It will only increase or stay the constant. That's it. Okay, so this completes the EM algorithm. So now what we will do now is we will see how to implement this EM algorithm for the case of the mixture densities that we saw. We will stop here and continue in the next lecture.